I wanted to learn anything. But anyway, okay. So for newcomers, welcome to Physics X. I always promise. God, I'm so nervous. I always promise that we start out crawling and then we end up going really fast at the end. Not fast, but it just like the level kind of goes like.
I think the phrase you used was it goes to Mach 8.
Mach 8, yeah, something special about Mach 8. So since many of you are here for the first time, I think I wrote up a first page of notes which are not directly connected to the topic we're going to talk about, but I think they'll actually be a good introduction for people who don't have a sophisticated physics background yet, and they're kind of a copy of something that I do in my particle physics class. So anybody who's taken particle physics from me, forgive me for repeating what you're about to hear. And as usual, if we don't get through everything today, which we probably won't, we will continue next time. That's the glory of this being just sort of a free-form class. So, to get started, the one statement I think we can all agree on is that spinners are weird. And some of you in the room might not even know what a spinner is, and I'm going to give you some idea of what spinners are right now, because you have to have some idea what a spinner is in order to understand what's going on next. So the example I give in particle physics to motivate spinners is getting you to think about something which you're all very comfortable with. So if I came along and I said, hey, how do you compute sine of theta? I think you all know how to do that, right? You get your calculator out, theta. You know, but how would you actually calculate that if you didn't have a calculator? What would you do? Well, how do we define? Oh, so I hear a lot of people saying Taylor series approximation. What's the right? So your first introduction to this, and the one that's the most concrete, is to say, okay, I know what I do. I go and I build a right triangle, one of whose angles is the angle theta in question, and then I literally take a ruler and I measure that length, and I measure that length, and then sine theta is just the ratio of those two things. And I keep wanting to put a bar on that H. But and literally that's how you can like concretely determine the sine of an angle, right? You build a triangle, measure two lengths, which you know how to do with a ruler, and then you just do division, which you all know how to do, okay? So this sort of preliminary, your earliest introduction to sine of theta, is rooted in this very concrete physical spatial definition that you immediately notice that it fails if I come along and say, okay, well, what about sine of I times theta? Where I is the imaginary number squared root of -1. I mean, what are you going to do? Build a triangle with an imaginary side? I don't know how to do that. Okay. So if this is the only definition of sine of theta that you have in your pocket, somebody coming along and saying, what's sine of I theta, this is going to be of no avail. Okay. Fortunately, this is not our only definition of sine of theta. We have another definition of sine of theta that we've encountered later in our, for example, calculus classes, and that is through a Taylor series. Through a Taylor series. So if instead of thinking of triangles as the definition of sine theta, we instead just allow ourselves to define sine of theta through its Taylor expansion, and most of you should know something about Taylor expansions at some point in your calculus class, right? Okay, so everybody's in Taylor expansions. Then if we, instead of using the triangle, use a Taylor expansion to define sine of theta, then we're in good shape. Because in the Taylor expansion, I can plug in a real value of theta, and then this is literally just an arithmetic operation. I'm multiplying things and adding them together. True, there's an infinite number of terms. It'll take a while, but there's nothing like impossible about the steps that I'm doing. Okay? And you all know the true power of this is that if theta is small enough, you can really get away with the first few terms because the rest of them get smaller and smaller. Okay? But the point is that you could just as well plug in an imaginary number times theta, and all of the operations on the right-hand side are still straightforward because you know how to square I, you know how to cube I, you know how to take I to any power. Okay? So by allowing yourself to get away from this geometric definition and replace it with something that's a little more abstract, you suddenly find that you can apply this thing to more contexts than you could using just that one definition. Okay? Now, what does this have to do with spinors? Well, in physics, you have dealt with a lot of things that are very intimately tied to space and coordinates. Okay, it's one of the first things we do in Physics 1. When we want to describe a problem, we say set up a coordinate system. And then a lot of the things you're working with are vectors. And one of the things I know about vectors is that, say, if we're in 3D with coordinates x, y, and z, just work with Cartesian coordinates, then the vector v we would write in terms of its components along each of the basis vectors pointing along the 3 coordinate directions. And if we wanted to change the coordinates, so if instead of working with, say, this x, y, and z, if we wanted to work with, say, an x, y, and z, let me get this way, which is maybe like this, or you can imagine I've taken this and I've rotated it to get here, then we have some new x prime, y prime, z prime. And what we can do is we can figure out what the vector components would look like in this new coordinate system. And the way that we do that is through just a 3x3 rotation matrix. Okay? So there's just some 3x3 matrix, and you treat this like a 3-component thing. It's got vx, vy, vz. And to get the new components, you multiply the original components by this 3x3 matrix, and that gives you the new vx, vy, vz. And then you can express the vector in a similar form. Okay? And then you've also encountered other quantities which kind of fall in the same family, and that family is what we refer to as tensors. The word tensor scares people the first time they see it. I remember when I was in Georgia Tech, this kid he wasn't even a physics major, but I was a freshman, and he was talking about Feynman's book on physics and how he's trying to read it. And he goes, and then I got to the calculation on tensors. It got really confusing. And I'll never forget, because this kid had really long, skinny fingers, and he was like, tensors. And that, for me, that's what a tensor was. It was his fingers going. And so I unnecessarily got very scared of tensors for a long time, and honestly never really learned much about them when I was an undergraduate, and became very familiar with them later on. But all tensors are is it's a big family of stuff that includes things you're familiar with. So for example, scalars. A lot of people just say a scalar is a number, but a scalar is something where if you change the coordinates, the scalar doesn't change. Okay, you encounter this in, for example, your calculus class when you first learn about vectors. You say vectors are different from scalars. So you have scalars, you have vectors, and then you have what are called higher rank tensors. And we don't have to go into the details of these tensors, although if you happen to be in my general relativity class, you are going to go into the details very soon. But higher rank tensors are just kind of, they're more generalism. They're more complicated versions of these. So if you might write a vector with a little superscript I, where this tells you which component you're looking at, a tensor might have 2 of these. Or it might have 3, with one of them being lower, or 4. Okay, or as many as you want. But anyway, the point is once you really understand what a vector is, getting higher rank tensors is just, it's an iterative process. There's nothing deeper. Okay, so tensors are not tensors. They're just fancier versions of vectors. Okay, so I say all this because the story that I just told you here is very, very analogous to the triangle story. Okay? That is, scalars, vectors, tensors, they're all rooted in this idea that I have a space or a space-time, I set up coordinates, I look at components of things that are associated with the coordinates, and then I can kind of transform things. This entire story is very rooted in space and spatial things. Like, you know, when we think about a vector, we think about, oh, it's an arrow and it points like that, although that's not the right definition of a vector. It kind of works It's something you can visualize in the same way you can visualize the triangle. It's hard to visualize a Taylor expansion, right? But if we want to explore all of the things that might be relevant in this story, we might have to get away from this coordinate leaning definition. So how do you do that? This is something which any physics major will eventually learn, and at varying degrees of effectiveness. But most of you will encounter it first in your quantum mechanics course. It doesn't have to be in a quantum mechanics course. But here is the quick and dirty on it. Okay, so right now we think of vectors as being intimately associated with these rotation matrices, these 3x3 rotation matrices that transform them when we change coordinates. Okay? In fact, there's a certain sense in which that's the definition of a vector. It is a thing which transforms under change of coordinates according to this rotation matrix. Okay? And you can similarly define higher rank tensors in the same way. So what I want to do is I want to take this rotation matrix and I want to kind of look at a more abstract definition of this. So what we can do is we can write that rotation matrix in what's going to at first seem like a very funny form. Okay? And those of you who took particle physics are like, I know where this is going. Okay? Where this is, of course, just the exponential. That's the imaginary number. And then there's GA theta A is the new thing. And what this GA and theta A are is pretty simple. GA, which is the set of G1, G2, G3. There are three of them. Induce rotations in the, let me get this right, the YZ plane, the ZX plane, and the XY plane. So I'm talking about 3 dimensions here. We're just talking about rotations, keeping it simple, okay? And when you talk about rotations in 3 dimensions, many of you think, oh, you can rotate around the x-axis, you can rotate around the y-axis, you can rotate around the z-axis. Any other rotation you can get by combining those 3. Okay? The correct way to think about rotations is not that you rotate around an axis, but rather that you rotate in a plane. Okay? And you actually have to think about it that way when you go beyond 3 dimensions. Because beyond 3 dimensions, there's not this natural association of a plane with a normal vector. Because in 4 dimensions, if you take a plane, there are 2 normal directions. So which one is it? So we talk about planes and not rotating around an axis. So these things induce the rotations in those 3 planes, and these are called the generators. And they are themselves 3x3 matrices. Okay. And then the theta A are, again, a set of theta 1, theta 2, theta 3. And these are just the angles by which you're rotating in each of those planes. That's it. So this little thing is the shorthand for take this generator and multiply it by that angle, take this generator, multiply it by that angle, this one times this one, and then add those 3 products up. Okay, so I could write that out, but it won't be very inspiring. If you do that, so literally take these 3x3 matrices, multiply each of them by the appropriate angle, add up the results, multiply by I, and then take the exponential of it, you will find that the resulting thing is just the rotation matrix that does whatever rotation that you're trying to describe in this way. Okay? So all I've done is I've taken the rotation matrices, which we associate with vectors, and I've written them in this kind of weird way. You might say, okay, so what? Who cares? But now I'm going to do something different. And this is my big, bold step. I'm going to define rotations with, instead of the rotation matrices, and by the way, for those of you who know a little bit of math, the rotation matrices form a set of things called SO3. Those are special orthogonal 3x3 matrices. It's not that important. If instead of defining my rotations with the R's, I'm going to define my rotations with the G's. And you might say, okay, so what? Okay. These are still 3x3 matrices. Actually, I'm not going to do it with the g's themselves. I'm going to do it with what is called the algebra of the g's. Got that?
Oh my god.
I know. Okay, so what do I mean by the algebra of the g's? Well, when I say an algebra in physics land, what I mean is that I take the g's and I commute them with each other. So what this means is I take GA times GB and then I subtract the reverse order. That's what the commutator is defined to be. And what I discover is if I'm working with the g's that are associated with rotations, that the relevant algebra looks like this. That is, if I take the commutator of two g's, I get I times, this thing is called the Levi-Civita symbol. It's a completely anti-symmetric 3-index object. All that means is if I take epsilon 1, 2, 3, and I call that plus 1, if I swap two of these, say this, then I get minus 1. If I make any of these things have the same value, say that, it's 0. From those sort of definitions, you can work out all the other possibilities for the epsilons. Understanding what I'm going to talk about today is not predicated on you really being comfortable with this, by the way. So Sal, you're okay. Okay, I'm just giving enough detail so that the people who know a lot are like, yeah, I remember that. And for the people who don't know a lot can be like, I'm going to learn that one day. So you're a broad audience, in case you haven't figured it out. Entertaining freshmen and grad students in the same room is not an easy task. Okay. So why do we call this an algebra? Well, I mean, you're multiplying things and you're getting things. I don't know. It's an algebra. And the specific name for it is a Lie algebra. And if you don't learn anything else in today's talk, that word is Lie, not lie. You go and give a presentation on Lie algebras anywhere, and you will get laughed off the stage. Okay, so this is the way we're going to define rotations. And the reason that that is powerful, so this is analogous to the Taylor expansion definition of sine theta. And the reason that that is very powerful is because I can find g's which satisfy this that are not 3x3 matrices. It turns out that there is a set of g's which exactly satisfy this same formula, but instead of being 3x3 matrices where everything in here is real, they're 2x2 matrices where the elements of the matrices are complex. Okay. Now, if I define my rotations here, these are rotations just as good as these are rotations. What's that, Flournoy? What are these acting on? Okay, we know in 3 dimensions a scalar has no components, or it has one component, it's a number. We know that vectors have 3 components. And then I'll just tell you, tensors have more. Okay? So how in the world are we getting something between a scalar and a vector? Like, what is this thing? Well, this thing is a spinner. In 3 dimensions, spinors are 2-component objects where each component is a complex number, and to transform them with rotations, I use these 2x2 complex matrices that I get using this set of g's. That is where you discover spinors in physics. You have to let yourself abstract your definition of rotations. You got to get away from coordinates and rotation matrices and everything being equal to the number of dimensions. You have to let yourself have this bit of mathematical machinery. But once you get here, the payoff is pretty cool. You get these objects which are being rotated, okay, in the same way that everything else is being rotated, but they're not 3-component things or 0 or 1-component things. They're literally these 2-component things, and they're complex. They're weird. Okay? Now, of course, the important question everyone should ask is, that's cool math. What does it have to do with the real world? Well, it has to do the following. It has the following to do with the real world. There are vectors in nature, right? We drive a car with a velocity that's described by a vector. Okay? There are particles in nature which have an intrinsic vector-like character. When you rotate, the particle itself acts like a vector. Okay? There are particles in nature which act like scalars. Most of the particles in nature act like spinors. In fact, everything you're made of acts like a spinor. Every electron, every quark. It's pretty much all you're made of is electrons and quarks. But all of those are spinors. So, have I convinced you that they're an important part of the physical world? Like, they're everywhere. And if you've ever heard the word fermion, that's what I'm talking about. A spin-a-half fermion is described by a spinor. They would be described by these little complex 2-component vectors. Okay? That was the review. Now let's get into the topic. Okay, so before I go on, are there any questions about this? Yes?
So is a spinor just a complex vector?
Well, I mean, when you say a complex vector, how are you defining the word
It looks
vector?
like a column vector that has complex
Well,
components.
so when you use the word column vector,
Yeah.
I think you're referring to the more abstract definition of a vector in like a math linear algebra class, where you just say, if I've got something that's a row or a column, I can call that a vector in a vector space, and I can talk about multiplying it by appropriate sized matrices. Those are linear transformations on the vector space. And in that sense, yes, this is a vector in a 2-dimensional complex vector space. Yes. What it is not, and this is where I should be really careful with my language, this is not a vector in space-time. Or in space. I'm not doing space-time yet. Because in space, a vector has 3 components, x, y, and z. This is not an x and a y component, or a y and a z component. These 2 things you can't point to and say that's x and that's y or anything like that. So there's a mathematical sense in which it's a vector, because it satisfies all the axioms of being an element of a vector space. But it's not a vector in space, where I think of space as x, y, and z, this room.
So it's just the interpretation of the indices of the vector is what makes it a spinor versus what we think.
Exactly,
of as a vector.
exactly. So I should say, in my discussion here, when I refer to vectors, I should be careful and say vectors in space,
Okay.
and then also vectors in space-time. If you just let yourself talk about vectors in the abstract, you can talk about vectors in any abstract vector space. Okay. So that is a fair assessment. Any other questions? Okay. All right. Awesome. Oh man. Oh man. Oh man. Oh man. So. Oh boy. It's about to get ugly. I just want to apologize. If I had known the audience that was going to be present, I might have aimed this a little bit differently, but it's too late. They're written, and we're just going to go.
Do what you did last time. Talk about how SUSY gets around, and it'll be
Oh boy. All right. So, supersymmetry, affectionately called SUSY, for those of you who are wondering, who is this SUSY? Who is this? Okay. So, supersymmetry is something that I talked about a year ago, almost, in Physics X, and there's a lecture online about it, so you're welcome to go back and look at that. I'm going to say a little bit about it today, because our ultimate goal is to talk about something called extended SUSY. But there's some background in this that you might appreciate by watching that video if you wander to the Physics X website. Have a look at it. Okay, so... Oh man. my God in heaven above. So, does anybody remember the Coleman-Mandula theorem? Yeah, that's what I thought. So the Coleman-Mandula... It's going to be okay. It's going to be all right. There's going to be a few things that hurt, and then otherwise we're going to get there. It's a good ending spot, I can tell you that, but it's just going to be a little bit of pain to get there. Okay, so here we go. The Coleman-Mandula theorem. Shake that head. So the Coleman-Mandula theorem asserts the following. In four-dimensional, now I am hitherto going to talk about four-dimensional space-time. I don't want to talk about space anymore because we're really thinking about fundamental things, so we should be talking about space-time together. So we live in a four-dimensional space-time. And in a four-dimensional space-time, in 4D quantum field theory, which, if you don't know what quantum field theory is, it's the sort of framework that we have that best describes fundamental physics. So the Standard Model, the Higgs mechanism, all of that stuff is described in the context of quantum field theory. We do not need to learn quantum field theory to really talk about it, to get what we're going to talk about. But in 4D quantum field theory, there is no possible extension of the space-time symmetries, which correspond to the Poincare group, which is defined as the semi-direct product of the translations in space and time with the Lorentz group. Based on the algebras. So I love to do this. I love to write things up, and then you all stare quizzically at them because you know about one word. So four-dimensional space-time, quantum field theory. This is just a way of doing physics. Don't worry about it. No possible extension means I'm going to give you something, and then you would like to add to it. And then this. What the? Okay. So if I'm doing particle physics and I say, what are the symmetries in particle physics, the space-time symmetries? Well, it turns out that this is the space-time symmetry. So let me explain to you what these mean. This right here means that if I'm working in rectangular coordinates, it means that I can translate in time and nothing changes. And we actually know that. We know if we do an experiment and then we do an experiment, the same experiment 10 minutes later, it should give us the same result. That's all that means. This, of course, just means if I do the experiment here where this is defined to be the x-axis, and then I do the experiment here, I should get the same result. Changing where the experiment is on the x-axis shouldn't change the answer. And so for y and z. So those are just the translations in space and time. This SO1,3 is complicated looking, but really all it boils down to is rotations in the various planes. So rotations in the yz plane, the zx plane, the xy plane, and then also rotations in planes that involve time. Because after all, space and time are put together. So when you draw your coordinates, you got to draw four things, x, y, z, and t. And then you can ask, well, what if I rotate in the tx plane? Okay, these things are what we more familiarly call boosts. So these rotations correspond to actually giving yourself motion in the x direction. That's not obvious, but that's the way it works out. So what we're describing here is basically special relativity. In special relativity, you can rotate the three coordinates, spatial coordinates, or you can boost. You can give yourself a velocity in the different directions. And what the Coleman-Mandula theorem says is that this is it. You can't add any other space-time symmetries based on Lie algebras, where the Lie algebra is that thing I used over here to define rotations. These also have Lie algebras. Okay? Well, what was discovered is that a theorem is only as powerful as its assumptions. And if you're willing to give up an assumption, sometimes you can evade a theorem. This is called a Nogo theorem, by the way. Nogo theorems just mean you can't do that. No, you can't go. And you can avoid this Nogo theorem by giving up the requirement of a Lie algebra. So remember, a Lie algebra is like what I wrote down for the rotation. generators. Generally speaking, this part right here can be different, but it's always going to be a commutator and then a generator over here. That's the important part about a Lie algebra. The most crucial thing is the commutator. Okay? It turns out that you can extend the space-time symmetries if you allow yourself an algebra that doesn't use a commutator, that uses something else, and that something else is an anticommutator, which, as the name might imply, you add the two permutations instead of subtracting. So remember, here you do GAGB minus GBGA. Here you just take them and you add them in the reverse order. So this thing right here is called an anticommutator. And the algebras that you get when you use anticommutators are, of course, not Lie algebras, but rather they are called Clifford algebras. Clifford algebras, if you're a Lie algebra kind of person. It's Clifford. Okay, all right. These are called Clifford algebras. All right. So what we discover is that we can add an extra symmetry into space-time, but it can't be like the rotation types of symmetries. And by the way, all of these are tied up with these Lie groups, even the translations and so forth. So, so what kind of things are represented by Clifford algebras? What kinds of things are Clifford algebras affiliated with? Any takers? Oh, don't Google it. Clifford algebras are intimately associated with spinors. Why do you think we spent so much time talking about spinors? So I won't have the time to go through how you get from a Clifford algebra to a spinor. That is done in detail in my particle physics course. All of those lectures are online, surprisingly enough. In fact, the most popular lecture in my entire particle physics course on YouTube is exactly the one that describes this. But you can go and look up details there, and you will also see a repeat of the triangle story. So, so what is happening here, and I'm going to say some words which some people might be familiar with, but others might not be, is here we have translations, and then we have, for example, rotations and then these boosts. And what we discover is that these symmetries are called bosonic symmetries. Now let me kind of give you some idea of why we say these are bosonic symmetries. So bosonic just means that it's associated with things that are either scalars or vectors or tensors. It's really bosonic means statistics, but there's this thing called the spin statistics theorem which connects those two ideas. So generally they're called bosonic symmetries. The name's not that important. What's important is to realize these are associated with things like scalars and vectors and so forth. And let me just give you an idea of how you can see that association. Translations in t, in x, and y, and z, these things are generated by the momenta in each of those directions. And when I say the word generated, you know what you might say, what are you talking about? Well, it's actually exactly that story I told you with the generators and the exponential and all that. The generators of translations, the g's, are really just secretly momentum components. And so if you talk about all four translations, they're generated by a four-component momentum vector. Okay? Say it again.
But what's the time moment? Because I'm familiar with this.
It's energy.
Okay.
Yeah, so a four momentum is actually the time-like component is the energy divided by c, and then px, py, pz. Okay. But it's a little easier if I just stick to the spatial story. The relativistic story gets a little weird. If you talk about this part of it, and I'm just going to look at the spatial part, the rotations are generated by, any guess? Angular momentum. Okay, we all learned about angular momentum. And what's so funny? Did I miss the joke? Sword?
I said spin.
No, Sword. Pay attention. So rotations are generated by angular momentum components. Kind of makes sense. Momentum components translate. Angular momentum components rotate. Okay. Again, angular momentum is a what kind of object?
Vector.
That's a pseudo-vector. We were close enough. You should know the difference, but it's kind of like a vector. Again, these are associated with vectors. These are associated with vectors. Everything here is associated with vectors. This new thing we're adding is not associated with vectors. It's associated with spinors. Okay? Now, this is where it gets hard, if it wasn't already. Conceptually, this gets hard for the following reason. When you, and I'm really speaking to people who have done a little bit of spinors in their past in their quantum mechanics class and so forth, you have gotten used to working with spinors as things that you transform. Yeah, they transform with a weird set of rules, okay? But that's your interaction with spinors. Supersymmetry deals with a different set of ideas. The set of ideas in supersymmetry is that the transformation itself is a spinor. And the transformation itself can act on spinors or scalars, vectors, whatever. So even if you're very comfortable with spinors, say from particle physics, that doesn't mean you're automatically comfortable. Matt's like, no one is comfortable with spinors. And I totally agree with you. No one is comfortable with spinors. Period. I'm not comfortable with spinors. They are weird. And they're hard. Because you can't see them. Well, you kind of can. But anyway. But you're literally working with a set of spinor transformations. And that is just a whole step of weird away from any work you've done in any physics class with spinors before. Okay? So you really have to kind of relax and just take it in. Okay, so fortunately, things are going to get less technical and more wordy, which is good for everybody. We have these transformations, and there's a lot that you can say about them. For example, I could write down what the Clifford algebra is. I could write down the full algebra of these, because what we're going to have is, well, shit. I'll just write it down, screw it. Because I'll refer to it later. It's painful, but you all want to know what it is, right? Tell me you want to know what it is. You want to see that algebra, don't you? Yeah, you really don't.
What's that?
Okay, so here we go. I'll just do this really quickly. So starting with this set right here, if we take the various momentum components and we form their commutators, we get 0 because components of momentum commute. If we take the generator of an SO13, which is going to be given by a 2-index matrix, and we take the commutator of that with a momentum component, which for some reason I put with a down index, for reasons which, if you follow index gymnastics, would make sense. Then you get something that looks like this, where that eta thing right there is the metric of Minkowski space. Again, it's a detail we don't have to worry too much about. And then, oh God. I'll write one and then just write junk. M nu sigma minus junk. There's like 4 more terms that look a lot like that one. Okay? What I've just written is this. It's the algebra for this part. I haven't talked about this at all. Okay? So different translations commute. Rotations and translations do not commute. If you translate and then rotate versus rotate and then translate, you will get different answers. Okay? And then rotations don't commute. And this is literally something you can see physically. If you take something and you rotate it, and then you rotate, do the rotations in the opposite order, you end up with a different configuration in general. Okay? So these algebras are just reflecting that. Now we're going to add in the new stuff. So first of all, the new part is going to be generated by this thing I'm going to call Q alpha. That's a spinner. Okay. Alpha is just a label that says this goes over the spinner components. These indices all go over coordinate components. So like that mu goes over t, x, y, z. Same with all of these other labels. This goes over the components of the spinner. They don't have anything to do with spacetime. Okay. If I take the commutator of a supersymmetry generating spinner with a momentum, I get 0. And now comes the anticommutators. If I take the anticommutator of 2 spinners, I get 0. And then confusingly enough, and this is why supersymmetry sucks, if I take the commutator of a spinner with its conjugate spinner, which we index by a dotted subscript, then I end up with an object that looks like this, which I just find annoying. So there's these dotted and undotted indices, there's conjugate spinners. What does that bar mean? What does that dot mean? Don't worry, we don't need to get into the weeds, but if you ever want to study supersymmetry, you are going to get into those weeds. I can guarantee you, and it's not fun, but it's just the reality. Okay, so that is the supersymmetry algebra.
So I see a lot of commutators defined. Why is that so much different than a Lie algebra then?
Those two.
Just because you add
Yeah, these are all Lie algebras. But that's before we've added supersymmetry. Supersymmetry is the Q. Now we can do a supersymmetry commutator with momentum, but it's really these anticommutators where you get the new love.
So the Clifford algebra contains the algebras.
Well, these are this is the algebra, 4 parts of which are Lie algebras, 2 parts of which are Clifford algebras. I wouldn't call the whole thing a Clifford algebra. Okay. Anything with commutators are Lie algebras, anything with anticommutators are Clifford algebras. Okay, so we kind of know about translations and rotations. We're all pretty comfortable with, what it means to translate something, what it means to rotate something. Okay, what are these supersymmetry transformations doing? All right. And if you want to figure out what supersymmetry transformations are doing, then what you're trying to do is study what is called the representations of supersymmetry. So to give you an idea of representation theory for transformations, I'm going to go to something that you should all be vaguely familiar with, if for nothing else than your chemistry class. I too hated chemistry. So when you studied chemistry and you were talking about spin, which I'm just going to call by this thing S, then one of the things that underlied a lot of the weirdness in chemistry was that if you take the spin of, say, the electron and you talk about its x component, its y component, and its z component, any pair of these things don't commute. Okay? And in quantum mechanics land, what that means is that you cannot simultaneously measure all 3 of these. It's fundamentally impossible to measure all 3 of these things at once. What happens is if you measure this, and then you measure this, if you go back and measure this again, you'll get a different value than you got the first time. So that's what it means that you can't literally measure them all 3 at the same time. Okay, so what we do is we create something which is called a Casimir invariant, which does commute with everything. So the simplest Casimir invariant in this case is just literally the square of the spin. So just the sum of the components squared. This thing you can measure, and then you can measure any one of these, and you can do those in different orders, and it's all okay. It doesn't matter what order you measure them in. Okay. Whereas here, Sx, Sy is not 0. Okay. So the way that we classify things in rotations and associated with a spin is we just pick one of these, and the conventional choice is z. And we say, okay, I'm going to give you the value of this, and then I'm going to give you the value of this, and that's pretty much all I can say about the spin. Can't say anything more. Okay. So the value of s squared tells us the representation that we're dealing with. And that word might sound weird, but it's actually pretty simple. If s squared is 0, then I'm dealing with what's called a scalar. If s squared is 1, then I'm dealing with what's called a vector. And if x squared happens to be a half, which is weird, I'm dealing with a fermion, or a spinor. And then I can talk about other values of s squared. Depending on the value of s squared, I get different possibilities for sz. So if the thing has no rotation, if it has no angular momentum at all, and I ask what's the z component of no angular momentum, what's the answer?
No.
It's 0. It'd be weird to get a component when you don't have anything to start with. Although I have to say in relativity, there are vectors which are non-zero, but whose magnitude is 0. Okay, if you are s squared equals 1, what are the possible values of sz?
Any number between 0 and 1?
Say it again?
Any number between 0 and 1?
Well, we're in quantum land.
0.
-1.
Yeah, it's 0 and plus and minus 1. And then for spin a half,
No. 0 plus minus 1 plus minus 1/2.
it's just plus minus half. It's okay. It's okay. I mean, if these are rules which at some level in some language you would have seen in chemistry, but they would have probably used completely, they would have talked about SPD, all that crap, okay? This is the story, this is part of the story that underlies it. So without getting caught up with what you do or don't remember, all I want you to realize is we have, so I'm talking about rotations here, just to give you a concrete example. When we want to talk about how things change under rotations, I have to first pick what I'm going to describe. Here I picked the magnitude and then one of the components. And then based on the magnitude, I get different behaviors under rotations. By the way, rotations don't change this because we know rotations don't change a scalar. Rotations change the value of this thing. So you could start with +1 and then you could do a rotation and make that into a 0 or make it into a -1. That's literally basically doing this. And then similarly here, a rotation can flip it from +1/2 to -1/2. All right? Okay, so the analogous story for supersymmetry, and again, we have no time to develop supersymmetry representation theory, is the following. The analog of this is a label which in the simplest case we call either a chiral supermultiplet or a vector supermultiplet. Those are just labeling like different things like this. The real interesting question is, in each of these categories, what are the possible outcomes of doing a transformation? And what we find is that in the chiral supermultiplet, we start with a spinor psi, and when we do the supersymmetry transformation, what comes out is a scalar phi. If we start with a vector supermultiplet, we start with a vector, and when we do a supersymmetry transformation, we get a spinor, lambda. Okay? So this is like a fermion, or spinor. This is a scalar. This is a vector. And then this is a fermion or a spinor. Now, if I'm using words which are not in the vernacular of everybody, when I say fermion or spinor, I'm literally talking about something with spin a half. So that's one of these things. A scalar has spin 0. A vector has spin 1. And then again, this is a spinor. So what the supersymmetry transformations are doing, which is weird, is they're actually changing the spin of these things. That does not happen with regular rotations or boosts or translations. If I start with a spin with a vector and I rotate it, I still get a vector. If I translate it, I still get a vector. But what these transformations are doing is they're literally changing the spin of the thing you're transforming. Now, how much are they changing it? If I go from a fermion to a scalar, how much did the spin change? It went down by a half. Similar here, spin 1 goes to spin a half, it went down by a half. So SUSY transformations reduce spin by 1/2. Okay? So if we take the standard model, which is our best description of nature, particle physics, and so forth, and we add supersymmetry to it, what we discover is the following. These things are all of the standard model matter. That is, everything you're made of. All the electrons, all the quarks, all the other more exotic things that you could be made of, like neutrinos or tauons or muons. All of the fundamental building blocks of stuff are these things. If you add supersymmetry to the story, for every one of these, you now get a partner scalar. Okay? These are called the sparticles. The supersymmetric particles. But who wants to say supersymmetric? That's like a $5 word. They're sparticles. And when you name them, you literally just throw an S onto the front of the associated particle. The selectron. This neutrino. The squark. The smuon. The stauon. The subquark. The stop quark. The charm quark. It gets weird, okay? So in the basic supersymmetry story, every particle in the standard model that you're made of gets one of these super partners, and that's where these names pop up. So you'll see these names if you ever encounter a story talking about supersymmetry. Now, in the standard model, what role do these particles play?
Mediator force.
The vectors in the standard model tell us about the forces. For each force, the electromagnetic, the weak nuclear, and the strong nuclear force, those forces are described by vectors. So this is the building blocks, and these are the forces that hold them together or make them interact. And so these are called gauge bosons. These, to indicate that they are the supersymmetric partners of gauge bosons, are called gauginos. You add ino to the end of it. And so we literally have the photino, the wino, the xeno, the gluino. Okay? They are spin-a-half particles associated to each of the force particles in the standard model. Okay? Now, there is, of course, one more particle in the standard model which I have not mentioned, and that is the Higgs. Were you going to say the Higgs?
Yeah.
She did
Bam!
say the Higgs.
She said the Higgs. I heard her. She said it before you met. Just got busted. And that's the Higgs. What kind of particle is the Higgs?
Boson.
It is a boson, but what's its spin? Anybody know?
0.
It is the only spin 0 particle in the standard model. Every other particle in nature is either spin a half or spin 1. The Higgs is the only spin 0 particle. The only spin 0 fundamental particle. You can take two things and combine them to make spin 0. But here I'm not talking about combinations of things. I'm literally talking about fundamental things. If you take the Higgs boson, then the way you actually get the Higgs is you start with a spinner, and then the supersymmetry transformation gives us the Higgs. And so you're kind of going backwards. You can think of it as an inverse supersymmetry transformation. And so in this case, we would call this the Higgsino. But it's really not that important. I'm just kind of giving you an idea of where these funky names are coming from. Okay? So what happens is that if you take the standard model with all the particles that we're made of and all the forces that interact between them and this crazy Higgs story, and you want to make it supersymmetric, you have to double the whole thing. Everything gets a partner. It's twice as big, it's twice as good. But you might ask yourself, where's gravity? What about gravity? Where's gravity? I know. Okay, so, well, truthfully, when we do standard model physics, when we build accelerators and we collide particles at high energies, we completely ignore gravity because gravity will not change the answer. You know, if I just take two electrons and hold them this far apart, the electromagnetic force between them is going to completely swamp the gravitational force between them. So the entire Standard Model and analysis and calculations are done completely ignoring gravity. But you can ask, can gravity get in the game? And it turns out, in supersymmetry, gravity gets in the game in a very interesting way. So, a very, very quick and dirty story, and I'm really going to do this heuristically with broad strokes, is the following. If I take a spinner, that two-component thing like an electron, and I just think about the fact that this is complex. So the spinner is, it's two-component complex thing. In addition to rotation things operating on it, I could also just imagine multiplying it by a complex number like e to the I theta. So that's something I could do to it. That's not a rotation, because a rotation would be a 2 by 2 matrix. If I multiply it by a complex number, then that's a different kind of transformation I can do on it. And so what this is doing is it's saying, I'm going to do the same transformation. I'm going to take all the spinners in the universe, and I'm going to multiply them by this one phase, this complex number. Physics in the universe doesn't change, doesn't care. Okay? Literally, like you can write down your physics, do this, it won't change. But you can do something really awesome, which is to take this and say, I'm going to take this number, and I'm going to let it change at different positions. I'm going to let it have a different value at different places and at different times. If you take all the spinners in nature and you multiply them by this, where you're multiplying by a different number at every different point in space and time, that's generally going to change the physics. But you can make your physics invariant under this. You can make your physics not care even if you do this. Now there's a recipe for doing that, and you learn about it a lot in particle physics. It's called making a gauge theory. And it turns out that if you do this, the result is electromagnetism. This is where electromagnetism comes from. And this is nothing but a gauge transformation in electromagnetism. It is, in a sense, the way you create electromagnetism, and it's also the way you create the other fundamental forces, by making a transformation be dependent on where you are, and say the physics has got to be invariant. Okay? Now the reason I say that is because you can ask yourself, these spinners are right now just constants. I'm taking a constant spinner and then I'm doing a transformation with it. But you can ask, what if I used a spinner which depended on position? What if I try to gauge supersymmetry? Well, you can make a theory that's invariant under supersymmetry transformations even when they depend on position. That's a gauge theory. But it comes with some baggage. You ready? If I'm going to let this depend on position, then this is also going to depend on position. These are very closely related things. But if these depend on position, this is just a number. That thing has to depend on position. But if that depends on position, then that has got to depend on position. So what I discover is if I try to gauge supersymmetry, I also have to gauge translations and rotations and boosts. Now let me explain to you what that means. When we think of translating something, we literally think about taking everything and just going like this. Every single thing goes like this. Okay? A gauged translation means I can take everything and each little part I can translate differently. And then the argument is, if I gauge translations, that theory won't change, even if you take every part of it and move it slightly differently. That's a weird theory, right? What do we call that theory? Say it again?
Gauge theory?
It is a gauge theory, but if I gauge translations and rotations, if I gauge these space-time symmetries. Now, people who do particle physics know that when we talk about gauge theories for the strong and the weak and the electromagnetic, we're doing transformations in this weird internal isospace. Here I'm actually doing space-time transformations, things like rotating vectors, but I'm going to gauge that. What do you think we get?
Gravity.
We get general relativity. We get gravity. So the act of trying to make supersymmetry local forces us to have gravity in the picture. So this leads us to what is affectionately called, or sweetly called, SUGRA, supergravity. Okay? So we got SUSY and SUGRA on the table. And if we add gravity to the game, then we have to take our particle story and we have to increase it by one more thing, and that is we have to include now the graviton, because gravity is in the game. Gravity has a particle associated with it, just like all the other forces. The graviton has spin 2. And if we apply the supersymmetry transformation to the graviton, we end up with an object which is really wonky. It's actually something which has a vector and a spinor index, which is a spin 3/2 particle called the gravitino. Okay. Okay, so I know I've given you a lot of this shit right here is just, it's terrifying, and I still don't know what that is. I mean, I know what it is, but it's unsettling to me to look at it. But what I want to sort of try and stress to you in the encapsulation of this, because this is really, really complicated. Honestly, like spinners are hard, and then you're talking about doing transformations that are built out of spinners. It's just weird. So you should ask yourself, is this worth it? Because yeah, I said, oh, if you gauge this, then you get gravity. You know, you can get gravity without supersymmetry just fine. So you should really ask yourself, is this worth it? What do you get? Okay? And I can tell you 2 things that you get out of doing supersymmetry. Okay? One of them I talked about the last time I talked about supersymmetry, and that is if we consider the electric charge, the strong charge, and the weak charge, the 3 charges of the standard model, technically they're couplings, then if we take those charges and we ask, how do those charges change as we slam things together at different energies? And yes, this is something which is going to fly in the face of what a lot of you think you know. The electric charge of an electron is not always the value you see in the book. If you ram an electron up to very, very high energy, its electric charge changes. Okay? No one tells you that, but that's the truth of it. And it turns out that if you take these 3 things and you look at how they all run with energy, they do something like this. Okay? They almost meet. It would be cool if they met, because if they all met at one point, then we could go, you know what? At that point, all of the 3 interactions are unified. And we talked about unification in the last semester of Physics X. So you can go watch the videos. Okay? Well, it turns out that if you add supersymmetry to the story, they do cross at a point. So supersymmetry, that's supposed to be a point. See? There's a black dot there. Your point is a point. It is a mathematical singularity. It's a point. This is, on the other hand, not a point. Therefore, adding supersymmetry to physics makes it more reasonable to think that the standard model, the fundamental forces of nature, somehow all come together into a single force. And then later on, you can also add gravity to them. Nathan, are you scratching your head or asking a question?
I was going to ask about gravity, but
yeah. Yeah. So gravity is not going to intersect at this same point. But gravity is so fundamentally different than the other forces, we actually wouldn't expect it to unify until a much higher scale anyway. Okay. This is what we would call GUT, grand unified theories, as opposed to theories of everything where you try to roll gravity into the story. Okay, so that's one thing supersymmetry gets you. Supersymmetry also gets you something else which is interesting, and it's a solution to what's called the hierarchy problem. And this is a little bit technical, but in the standard model, there is only one particle in the entire standard model that has a fundamental mass. That is, like, it literally is born in the universe with a mass. Everything else is born with no mass and then gets mass through the Higgs mechanism, that famous thing that was discovered in 2013. Well, the mechanism was discovered like 34 years ago, but the particle of that mechanism was found. So the only particle in all the standard model that actually genuinely has a fundamental mass is the Higgs itself. Because the Higgs doesn't get its mass through the Higgs mechanism. It's like masturbation. I'm going to give myself some mass! No, you can't do that. That was a wildly inappropriate. That Not because it was offensive, but because it was wrong. So many levels. But anyway, so the Higgs mass is the only mass in the Standard Model that we might worry about. Like, what's its value? Is it the thing that it should be? And, well, guess what, folks? In the same way that charges change with energy scale, so do masses, in particular the Higgs mass. If you look at the Higgs mass at different energies, and yes, folks, I'm saying the electron mass changes with energies too. I shit you not. Okay? But if you look at the Higgs mass, you actually discover that the Higgs mass grows very, very large, larger than what we observed, as you go to higher and higher energies. So the question is how do we keep the Higgs mass from blowing up and keep it down to the level it should be? And just to cut to the chase, supersymmetry saves the day, because when you have supersymmetry and you're calculating how the Higgs mass changes, it turns out that you get a diagram for the, I mean, this is alluding to something that, it's a way we calculate things in particle physics, but you get a picture and you calculate, there's an integral associated with this, you calculate that integral, and then that tells you how the Higgs mass changed. When you add supersymmetry, you get a new diagram where if this was a scalar, this is a spinor. Remember, we double the particles? But what's interesting is if this contribution comes in with a plus sign, this contribution comes in with the same magnitude, but with a minus sign. So when you add up a bunch of stuff and it makes the Higgs mass blow up, adding supersymmetry adds in exactly what you need to cancel the things that are blowing up. So supersymmetry actually solves the hierarchy problem. And that was one of its principal motivations for being researched. Oh my God. Okay, so it's now 7:10, and I have 5 pages of notes. So I'm going to stop. Yes. I don't want to lose you all. Yes. But I want to end. Let me end with one more comment, and this is going to motivate. This is going to motivate where things go next. So supersymmetry did 2 really great things for us. It makes unification seem like a reasonable thing, and it solved this technical problem with the Higgs mass. Okay. But then you can go back and say, well, what about supergravity? What about gravity? What about quantum gravity? Quantum gravity is, after all, like the sort of holy grail. And one of the things about quantum gravity is, if I take the Standard Model and I just say, okay, I'm going to do gravity. I'm going to take into account the fact that things do attract gravitationally. I'm going to treat the gravity with quantum mechanics. Just good old quantum mechanics that we're used to. If I do that, and I'm working with the Standard Model as the stuff, and then there are the other forces, this gets infinities that won't go away. The technical language for it is that we cannot renormalize quantum gravity. There's not a systematic way to explain where those infinities are coming from. And the renormalization is a really beautiful, very deep story in nature. And I alluded to parts of it in previous talks. But you might say, well, hey, wait a minute. Supersymmetry helped these infinities. Maybe it can help these infinities, and in fact, it doesn't. It doesn't. So while supersymmetry provides some cancellations of things getting big, it doesn't cure the infinities that arise when we add gravity to the story. But, and I'm going to end here, all of that is predicated on the idea that there was only one of those. There can only be one. Could we consider adding in more?
Spinners?
More spinners. If we add more spinners, then we get more transformations. If we get more transformations, we get a lot of new and interesting stuff. That is what extended supersymmetry is. What I have told you today is basically the story of n = 1 supersymmetry. N = 1 meaning there's only one of these. Next time we meet, we're going to talk about n equals 2 supersymmetry. And we're going to see the things that change. And you actually get, in addition to a lot of interesting things, you actually get some benefits in terms of cancellations. But you know what? Why stop at 2? So we'll go beyond 2. And we'll find some very fascinating results. But then, since we're freeing our minds, we're going to decide, why stick with 4 dimensions? Why not go to 5 dimensions and 6 dimensions and 7 dimensions? So next time we'll talk about what happens when you make the supersymmetries bigger, and then what happens when you actually look at it in different numbers of space-time dimensions. And the punchline of that story is going to be M theory. It's got Madison excited. So we're genuinely at the end of this going to make a connection to string theory and M theory, these things which you might have heard of, okay? And they actually arise very naturally in carrying this story to its logical conclusion. But we'll have to do that next time. Thank you all for coming. I hope that wasn't too intimidating. In the future, we can pick topics or I'll write things maybe at a more accessible level. On the other hand, in principle, our next meeting would be next Monday. But who's planning on being on campus next Monday? It's a holiday.
Recovering from airplanes.
No, we get home Sunday.
All right.
Sundays before Monday.
Sunday is before Monday.
Raise your hand if you would be here next Monday.
Is it 6?
At 6.
Okay.
Yeah, I mean, I don't know if I want to come in on Monday.
It's like, I know what you want.
No.
Huh?
Like, I know you love this stuff, but it's like, I don't really want to teach us about it.
Okay, I think we're going to wait 2 weeks, let that sink in. Again, I'm going to put the lecture online along with the notes, so you can go to the PhysicsX webpage and review this. And I want to stress to you all, if I'm writing things on the board that are kind of going, it's okay, because many of you might study this one day, but I hope there's sort of a broad strokes lesson of what's going on. Maybe one day we'll get you to try and study some of this in more detail.
So is next time more extended SUSY, or is it actually?
It is extended SUSY.
Okay.
It's extended SUSY, so it's the continuation of this, which we actually could have gotten to if I didn't do my triangle Lie algebra intro. But